Hello, welcome to the video lecture series on digital image processing. For last few lectures, we were discussing about image segmentation operations and image analysis operations. So, in our last lecture, we have talked about the discontinuity based image segmentation. We have seen earlier or we have discussed earlier that there are mainly two approaches of image segmentation. One is the discontinuity based image segmentation and the other one is similarity based image segmentation. For last two classes, we have talked about the discontinuity based image segmentation, and in discontinuity based image segmentation, we have seen that the segmentation is done using the characteristics of variation of intensity values when there is a variation of intensity from say background to a foreground object. So, under this we have seen various point and line and edge detection operations which are used in this segmentation process. Here the basic purpose was that an object is to be described by its boundary or its enclosing boundary, which are to be obtained using one of these discontinuity based operations. And we have discussed that though we want that the object boundary should be continuous or it should have a complete definition, but because of noise or maybe because of non-uniform illumination, after performing these different edge detection operations, the edge points that we get, they are not normally continuous. So, to take care of this problem, after this edge detection operation, the edge points that we get, they are to be linked. So, for that we have discussed about two different approaches. One is local linking operation, where the edge points in the neighborhood are linked together if we find that those two edge points are similar in nature. And for that, as similarity criteria, we have taken the strength of the gradient operator or strength of the edge operator, as well as the direction of the edge at those points. So, if we find that within a neighborhood, two edge points have the similar edge strength and also they have similar edge direction, in that case those two points are linked together to be part of the same edge. Now, here again the problem is that if the points are not in the small neighborhood which is defined, but the points are at a larger distance, in that case this local edge linking operation does not help. So, in such cases what we have to go for is the global edge linking operation. So, we have discussed a technique that is Hopf transform. So, using Hopf transform, we have been able to link the distant edge points, and this is an operation which is called global edge linking operation, or it is the global processing technique. Now, today we will start our discussion on the other type of segmentation, which is the similarity based segmentation. So, under similarity based segmentation, there are mainly three approaches. One is called thresholding technique, the second approach is region growing technique, and the third approach is region splitting and merging technique. Under thresholding technique, again we have four different types of thresholding. One is called global threshold, the other type of thresholding is called dynamic or adaptive thresholding. There is something called optimal thresholding, and there is also a thresholding operation which is called local thresholding. So, we will discuss about these different region based segmentation operations, either thresholding or region growing and the region splitting and merging techniques one after another. Now, let us first start our discussion with the thresholding technique. So, first we will discuss about the thresholding technique for segmentation. Now, thresholding is one of the simplest approach of segmentation. Suppose we have an image, and as we have said earlier that an image is described by or represented by a two-dimensional function f x y. And let us assume that this image contains a dark object against a light background. So, in such cases, if there is a dark object against a light background, or even if it is the reverse, that we have a light object against a dark background, then you will find that the intensity values, they are mainly concentrated near two regions, or we call them two modes. One of the region will be towards the darker side or towards the lower intensity values, and other mode will be towards the brighter side or towards the higher intensity values. So, if you plot the histogram of such a image, so here we are assuming that we have one object and let us assume that the object is brighter and the background is dark. So, if we plot the histogram of such an image, the histogram will appear something like this. So, on this side we put say intensity value z, and this side says our histogram of z. So, as we said that because we are having one object and we are assuming that the object is bright, which is placed against a dark background. So, the intensity values will try to be accumulated, will the histogram will give rise to a bimodal histogram, where the intensities will be concentrated on dark side as well as on the brighter side. So, for such a bimodal histogram, you find that there are two peaks, one peak here and the other peak here, and these two modes or these two peaks are separated by a deep valley. So, this is the valley and this is one peak and this is the other peak, and as we have assumed that our object is bright and the background is dark. So, all these pixels which are grouped in the lower intensity region, these pixels belong to background and the other group of pixels, they belong to the object. Now, the simplest form of segmentation is if we can choose a threshold value say t in this valley region, and we take a decision that if a pixel at location x y or have the intensity value f x y, which is say greater than t, then we say that this pixel belongs to object, whereas if f x y is less than or equal to the threshold t, then this pixel belongs to the background. So, this is our simple decision rule, which is to be used for thresholding purpose. So, what we have to do is we have to choose a threshold in the valley region and then check the image. The segmentation is simply testing each and every pixel to check whether its intensity value is less than the threshold or the intensity value is greater than the threshold. So, if the intensity value is greater than the threshold, then we will say that the pixel belongs to an object, whereas if the intensity value is less than or equal to threshold, we say that the pixel belongs to the background. Now, the situation can be even more general, That is, instead of having a bimodal histogram, we can have multimodal histograms. That is, our histogram can even be of this form. Like this. So, this is our pixel intensity Z, and on this side is the histogram. So, here you find that the histogram has 3 different modes, which are separated by 2 different values. So, now what we can do is we can choose one threshold, say T 1 in the first valley region and the other threshold T 2 in say second valley region. So, what this histogram indicates is that there are 3 different regions or 3 different intensity regions, which are separated by some other intensity band. Okay. And those 3 different intensity regions are represented or gives rise to these 3 different peaks in the histogram. So, here our decision rule can be something like this, that if we find that the intensity value f x y at a pixel location x y is greater than threshold T 2, then we say that the point x y belongs to say object O 2. So, all the intensity values, all the pixels having intensity values greater than T 2, these pixels we say that they belong to the object O 2. In the other case, if a pixel has an intensity value in this region, that is greater than T 2, greater than T 1 and less than T 2, then we will say that this particular pixel belongs to object O 1. So, our decision rule will be that T 1 less than f x y less than or equal to T 2, then this indicates that the corresponding pixel x y, it belongs to object O 1. And obviously, the third condition will be that if f x y, the intensity value at a location x y is less than threshold T 1, in that case we say that the corresponding pixel x y, it belongs to the background. So, even in cases we can have histograms which are even which will have even more number of peaks, more than 3 peaks. Such cases also similar such classification is possible. But what we have to do for this thresholding based segmentation technique is that we have to choose proper threshold values. Now, this threshold value or the thresholding operation can be considered as an operation that involves testing against a function t, where this function t is of the form t is equal to t x y p x y and f x y. So, this thresholding operation, what we are doing is we are considering, or this can be viewed as an operation to test the image pixels against a function t, where this function t is of this form. This function t is a function of x y, which is nothing but the pixel location in the image, f x y, which is nothing but the intensity value at location x y. So, this is pixel intensity at location x y, and p x y, it is some local neighborhood property, in a neighborhood centered at x y. So, in general this threshold t is a function, can be a function of pixel location, the pixel value as well as the local property within a neighborhood around a pixel location x y. So, any combination of these three, that is pixel location, pixel value and neighborhood property. This neighborhood property can even be the average intensity values within a neighborhood around pixel x y. So, any combination of this t can be a function of any combination of these three terms, and depending upon the combination, this t can be either a global threshold or a local threshold, or it can even be an adaptive threshold. So, in case the t is the threshold t is only a function of f x y, we say that the threshold is a global threshold. Whereas, if t is a function of f x y and the local property, that is p x y, then we say that the threshold t is a local threshold. And if in addition to all this, t is also a function of the location of the pixel, that is, in the more general case, if t is a function of x y, f x y as well as p x y, then we say that this threshold t is an adaptive or dynamic threshold. Now, whichever the nature of the threshold t is, whether it is local or global or adaptive, our thresholding operation is by using this threshold, we want to create a thresholded image, say g x y, from our input image f x y, and we set the value of g x y is equal to 1 if the corresponding function or the intensity of the image at that location, that is f x y, is greater than the threshold t. Now, this threshold t can be either global or local or adaptive, and we set g x y is equal to 0 if f x y is less than or equal to the chosen threshold t. So, you find that the basic aim of this thresholding operation is we want to create a thresholded image g x y, which will be a binary image containing pixel values either 0 or 1, and this value will be set to 0 or 1 depending upon whether the intensity f x y at location x y is greater than t or it is less than or equal to t. So, if we have a bright object against a dark background, in that case g x y equal to 1, this indicates that the corresponding pixel is an object pixel, whereas g x y equal to 0, this will indicate the corresponding pixel is a background pixel. On the contrary, if we have dark objects against bright background, in that case what we will do is we will set g x y equal to 1 if f x y is less than or equal to t, again indicating that in the thresholded image a pixel location having an intensity value of 1, that indicates the corresponding pixel belongs to the object. And in such case, we will put g x y equal to 0 if f x y is greater than t, again indicating that a pixel in the thresholded image g x y, if it is equal to 0, the corresponding pixel is a background pixel. Now, the question is how to choose this threshold value. Now, for that let us come to the case again considering the histogram. We have said that if my histogram is a bimodal histogram of this form, then what I can do is by looking at the histogram. So, this is our intensity value z, and on this side we have h z. By inspecting this histogram, we can choose a threshold in this deep valley region, and using this threshold I can go for the segmentation operation. Now, by doing this, I will show you one particular result. Say for example, in this particular case, here you find that we have an image where the objects are dark, whereas the background is bright. So, naturally in this case I will have a histogram where the histogram will be a bimodal histogram. So, the nature of the histogram will be like this. So, this will be a bimodal histogram. So, here if I choose a threshold t in this region and using this threshold I segment this image, then the kind of segmentation that we get is as given here. So, here you find in the second image, in the segmented image, that your background and object regions have been clearly separated. Even the shadow which is present in the original image, that has been removed in the segmented image. So, this segmentation, though it is a very simple operation, if you choose the threshold in the valley region between the two modes in a bimodal histogram, then this segmentation, this simple segmentation operation can clearly take out the object regions from the background. But here what we have done is, we have chosen the histogram to choose the threshold, that is, you inspect the histogram and then from inspection of the histogram you have to choose the threshold value. But is it possible to automate this process? That is, instead of finding the histogram by instead of finding the threshold value by looking at the histogram, can we automatically determine what is the threshold value which should be used for segmenting an image? So, this operation can be done by using an iterative procedure. So, automatic threshold So, here again for detecting this threshold automatically, what we can do is, we can first choose an initial value of threshold. So, arbitrarily or by or somehow we can choose an initial value of threshold, and using this initial value of threshold, what we can do is, we can have a segmentation of the image. So, when you segment the image using this initial value of threshold, the segmentation operation basically will partition your histogram into two partitions, or the image will be divided into two groups of pixels. So, we can say that one group of pixels we term them as group G 1 and the other group of pixels we term them as group G 2. So, the pixel intensity values in group G 1 will be similar and the pixel intensity values in group G 2 will also be similar, but these two groups will be different. Now, once I separate or partition the image intensities into these groups G 1 and G 2, the next step that what we will do is you compute the means or the average intensity values mu 1 for group G 1 and the average intensity value mu 2 for group of pixels G 2. So, once I get this mu 1 and mu 2, that is the average intensity value in the group of pixels G 1 and also the average intensity value for the group of pixels G 2, then in the fourth step what I do is I choose a new threshold T which is equal to mu 1 plus mu 2 divided by 2. And after doing this, you go back to step 2 and perform the operation thresholding operation once again. So, what we are doing is we are choosing an initial value of threshold. Using that initial value of threshold, we are thresholding the image. By thresholding, what we are doing is we are separating the intensity values into two groups G 1 and G 2. For group G 1, I find out the average intensity value mu 1. For group G 2, I also find the average intensity value G 2. Then I find out a new threshold which is the mean of these two averages, that is mu 1 plus mu 2 by 2. And using this new threshold, I threshold the image again. So, thereby these groups G 1 and G 2 will be modified. And I repeat this process, that is thresholding to grouping, then finding out the intensity averages in the two different groups, two separate groups, recalculating the threshold. This entire process will be repeated until and unless I find that the variation in two successive iterations in the computed value of t is less than some pre-specified value. So, this operation has to continue until you find that in one iteration t I and the next iteration t I plus 1, the threshold value in the ith iteration t I and in the I plus first iteration t I plus 1, the difference between these two is less than or equal to some pre-specified value, say t prime. So, when I attain this condition, I stop my thresholding operation. So, here you find that we do not have to go to the histogram to choose the threshold. Rather, what we do is we choose some initial value of threshold, then go on modifying this threshold value iteratively. Finally, you converge, you come to a situation where you find that in two subsequent iterations, the value of the threshold does not change much. And at that position, whatever the thresholded image that you have got, that is your final thresholded value. So, using this kind of adaptive threshold, the kind of result that can be obtained is something like this. So, here you find that this is one input image and you can identify this that this is a fingerprint image. This is the histogram of that particular image. So, obviously, in this from this histogram also I can choose a threshold somewhere here. But this thresholded output that has been obtained is not by choosing a threshold from the histogram, but this is by automatic threshold selection process, that is by doing this iterative process. And it can be observed that from this histogram, whatever threshold you chose, by this automatic process, the threshold will be similar to that. And here you find that since the threshold that you have chosen, this does not consider the pixel location or the local neighborhood of the pixel intensity values, Here the threshold is a global one, that is, for the entire image you choose one particular threshold, and using that threshold you go for segmenting the image. So, the kind of thresholding operation that we have done in this particular case, this is called a global thresholding operation. Now, you find that in this particular case, this global thresholding will give you very good result if the intensity or the illumination of the scene is uniform. But there may be cases where the scene illumination is non-uniform, and in case of such non-uniform illumination, getting a global threshold which will be applicable over the entire image is very difficult. So, let us take one particular example. So, in this particular case, on the top we have an image, and you can easily find out that for this image, if I plot the histogram will be as shown on the right hand side. Clearly, this histogram is a bimodal histogram, and there is a valley in between the two modes. So, these two modes are separated by a deep valley. So, obviously, for such a kind of histogram, I can always choose a threshold inside the valley and segment this image successfully. But what happens if the illumination is not proper? If the background illumination is not uniform, then this image, because of this non-uniform illumination, may turn out to be an image like this. And whenever I have such an image with poor illumination, and you find that the histogram of this image appears as given on the right hand side. And here you find that though the histogram appears to be a bimodal one, but the valley is not well defined. So, this simple kind of thresholding operation or the global thresholding operation is likely to fail in this particular case. So, what should we do for segmenting this kind of images using the thresholding operation? Now, one approach is you subdivide this image into a number of smaller sub images, assuming that in each of these sub images the intensity will be more or less uniform, or the illumination is more or less uniform, then for each of the sub image we can find out a threshold value. And using this threshold value, you can threshold the sub images, and then the combination of all of them or the union of all of them will give you the final thresholded output. So, let us see what we get in this case. As we said that for this kind of images where the illumination is non-uniform, if I apply a single global threshold, then the kind of output, the thresholded output that we are going to get is something like this. So, here you find that the thresholding has failed miserably, whereas if I subdivide this image into a number of sub images as given on this left hand bottom, and then for each of these sub images I identify the threshold, and using that threshold you go for segmenting that particular sub image, and the thresholded output that you get is given on this right hand side. Here you find that excepting these two, rest of the sub images have been thresholded properly. So, at least your result is better than what you get with a global threshold operation. So, now because we are going for a threshold, selection of a threshold which is position dependent, because every sub image has a particular position. So, now because this threshold selection is position dependent, it becomes an adaptive thresholding operation. Now, let us try to analyze that why this adaptive threshold has not been successful for these two subregions. So, if I look at the nature of the image, here, if you look at this top image, you find that in this top image here is a boundary, okay, where this small portion belongs to the background and this large portion of the image belongs to the object. Now, if I plot the histogram of this, the histogram will be something like this. Because the number of pixels in the background is very small, so the contribution of those pixels to the histogram that is within this region is almost negligible. So, instead of becoming a bimodal histogram, the histogram is dominated by a single peak, and that is the reason why this thresholding operation has not given good result for this particular subregion. So, how to solve this problem? Again our solution approach is same. You subdivide this image into smaller subdivisions. So, you go for subdividing further, and for each of these smaller subdivisions, now you try to find out the threshold and segment each of the subdivisions with each of the subdivisions using this particular threshold. So, if I do that, you find that the kind of result that we get is here, and here the segmentation output is quite satisfactory. So, if the scene illumination is non-uniform, then a global threshold is not going to give us a good result. So, what we have to do is we have to subdivide the image into a number of subregions and find out the threshold value for each of the subregions and segment that subregion using this estimated threshold value. And here, because your threshold value is position dependent, it depends upon the location of the subregion. So, the kind of thresholding that we are applying in this case is an adaptive thresholding. Now, in all these thresholding, whether it is a global thresholding or adaptive thresholding that we have discussed so far, none of these cases we have talked about the accuracy of the thresholding or how accurate or what is the error that has been involved, that is by this thresholding process. So, we can go for a kind of thresholding by making use of some statistical property of the image, where the mean error of the thresholding operation will be minimum. So, that is a kind of thresholding operation which is called optimal thresholding. So, what is this optimal thresholding? Again, let us assume that the image contains two principal gray levels, intensity regions, one intensity region corresponding to the object and the other intensity region corresponding to the background. And we use a variable and we assume that these intensity variables can be modeled as a random variable, and this random variable is represented by a variable say z. Now, once we represent the random variable by this z, then the histogram of this particular image or the normalized histogram can be viewed as a probability density function of this random variable z. So, the normalized histogram can be viewed as a probability density function p z of this random variable z. Now, as we have assumed that the image contains two major intensity regions, two dominant intensity values. So, our histogram is likely to be a bimodal histogram. So, the kind of histogram that we will get for this image is a bimodal histogram. So, it will be something like this or yeah. And as we said that the histogram we are assuming to be a probability density function of the intensity variable z. So, this bimodal histogram can be considered as a combination of two probability density functions or combination of two PDFs. Okay. So, one of them is say probability distribution function P 1 z, the other one is probability density function say P 2 z. So, P 1 z indicates the probability distribution function, the probability density function of the intensities of pixels which belong to say background, and P 2 z is the probability density function of the pixel intensity values which belong to say object. Now, this overall histogram, that is P z, can now be represented as the combination of P 1 z and P 2 z. So, this overall P z we can write as capital P 1 into P 1 z plus capital P 2 into P 2 z, where this capital P 1 indicates the probability that a pixel will belong to the background, and capital P 2 indicates the probability that a pixel belongs to an object. So, obviously, this capital P 1 plus capital P 2, this will be is equal to 1. So, these are the pixel probabilities which belong to either foreground or the background. So, here our assumption is that we have a bright pixel against a dark background, because we are saying that capital P 1 the capital P 1, it is the probability that a pixel belongs to the background, and capital P 2 is the probability that a pixel belongs to the foreground or the object. Now, what is our aim in this particular case? Our aim is that we want to determine a threshold t which will minimize the average segmentation error. Now, you find that since this overall probability is modeled as a combination of two different probabilities. So, it is something like this. I can say that I have one probability distribution function which is given by this, and the other probability distribution function is say given by this, so that my overall probability distribution function is of this form. This is my overall probability distribution function. So, this blue color, this indicates P 2 z, and the pink color, this indicates P 1 z, and the yellow color indicates my overall probability density function, that is P z. Okay. So, in this particular case, if I choose a threshold t somewhere here, so this is my threshold t, and I say that if f x y is greater than t, then x y belongs to object. Okay. Now, here you find that though we are taking a hard decision that if f x y is greater than t, then x y belongs to object, but the pixel with intensity value f x y also has a finite probability, say given by this, that it may belong to the background. So, while taking this decision, we are incorporating some error. The error is the area given by this probability curve for the region intensity value greater than t. So, the probability of considering a background point as an object point, or the error leads to an error, okay, that is a background point may be classified as an object point. So, the error that you encounter in that particular case is given by say E 1 t, because this error is threshold t dependent. So, write this as E 1 t is equal to say P 2 z d z, take the integral of this minus infinity to infinity. So, what is this? This is the probability that this is the error incorporated, that an object pixel may be classified as a background pixel. Similarly, If a background pixel is classified as an object pixel, then the corresponding error will be given by E2t is equal to integral P1z dz, where the integral has to be taken from t to infinity. So, this gives you the two error values. One of them gives the error that you encounter if you classify a background pixel as an object pixel, and the other one if you segment a object pixel as a background pixel. So, from these two error expressions, the overall error probability can now be represented as E t is equal to capital P 2 into E 1 t plus capital P 1 into E 2 t. So, you find that this E 2 was the probability, it was the error of classifying a background pixel as a foreground pixel, and E 1 t was the error of classifying an object pixel as a background pixel, and P 1 is the probability that a pixel belongs to background, and capital P 2 is the probability that a pixel belongs to the object. So, the overall probability of error will be given by this expression capital P 2 into E 1 t plus capital P 1 into E 2 t. Now, for minimization of this error, what you have to do is, we have to take the derivative del E t del t and equate this to 0. So, whatever is the value of t that you get, that is what is going to give you the minimum error. So, if I put this restriction, then this above expression, we are not going into the details of mathematical derivation, I will just give you the final result. This can be given by capital P 1 into P t P 1 t plus capital P 2 into P 2 t. Sorry, this is not plus, this is equal. So, we are going to get an expression of this form, and the solution of this equation gives the values of t. So, if we try to solve this, you find that what I need is the knowledge of this probability density functions P 1 t and P 2 t. So, as we know that in most of the cases, we normally assume the Gaussian probability density function. So, if I assume that Gaussian probability density function, in that case the overall probability P z is represented by capital P 1 divided by square root of 2 pi sigma 1 e to the power minus z minus mu 1 square by 2 sigma 1 square plus capital P 2 by square root of 2 pi sigma 2 e to the power minus z minus mu 2 square by 2 sigma 2 square, where mu 1 is the average intensity value of the background region and mu 2 is the average intensity value of the object region, and sigma 1 and sigma 2 they are the standard deviations of the intensity values in the background region and the intensity values in the object region. So, by assuming this Gaussian probability density function, we get the overall probability density function as given by this expression. And by assuming this, and then from this particular expression, the value of t can now be found out as the solution for t is given by a solution of this particular equation a t square plus b t plus c is equal to 0, where this a is equal to sigma 1 square minus sigma 2 square, B is equal to 2 into mu 1 sigma 2 square minus mu 2 sigma 1 square, and C is given by sigma 1 square mu 2 square minus sigma 2 square mu 1 square plus 2 sigma 1 square sigma 2 square ln sigma 2 capital P 1 by sigma 1 capital P 2. And here, if we assume that sigma 1 square is equal to sigma 2 square is equal to say sigma square, then the value of the threshold t comes out to be t is equal to mu 1 plus mu 2 divided by 2 plus sigma square upon mu 2 mu 1 minus mu 2 ln capital P 2 divided by capital P 1. So, this is a simple expression for the value of threshold that we can obtain in this optimal thresholding operation. And this is optimal in the sense that this value of the threshold gives you minimum average error. And here again you find that if the probability the capital P 1 and capital P 2 they are same, in that case the value of t will be simply mu 1 plus mu 2 by 2, that is the mean of the average intensities of the foreground region and the background region. Okay. So, as we said that by estimating a threshold by this process, if we segment the image, then the average error of segmentation will be minimum, that is minimum number of foreground pixels will be classified as object pixels and minimum number of object pixels will be classified as foreground pixels. Now, let us see an example that why this optimal thresholding can give us good results. Let us take a very complicated case like this. This is the cardiogram angiography, in which the purpose is to detect the ventricle boundaries. Okay. You find that the image that is given here is very complex, and though we can somehow figure out that there is a boundary somewhere here, but it is not very clear. So, the approach that was taken is this image was divided into a number of sub images. For every sub image, the threshold was estimated, the optimal threshold was estimated, and then the thresholding was done. So, for this optimal thresholding, what was done is for each of the sub images, say for example, this was divided into a number of sub images like this. For each of the sub image, what was computed is the histogram, and the threshold was computed for those sub images which shows a bimodal histogram like this. Whereas, you find that if I take a sub image here, this normally shows a unimodal histogram which is given here. For these sub images no threshold was detected, the threshold was detected only for those sub images which showed bimodal histogram. And the threshold for other sub images were estimated by interpolation of the threshold of the regions having bimodal histogram. And then a second level of interpolation was done, iteration was done to estimate the threshold value at each of the pixel locations. And after doing that, for each pixel location using that particular threshold, the decision was taken whether the corresponding value should be equal to 0 or in the thresholded image the corresponding value should be equal to 1. So, using this the thresholded image was obtained, and the boundary of such thresholded image when superimposed on this particular image, you find that this one shows the boundary of the thresholded image. So, as was estimated that this was the estimated boundary, the boundary points are quite well estimated in this particular case. So, with this we stop this particular lecture on thresholding operations. Thank you.